Greetings boys and greetings girls. In this video I am going to do some implementation of the Powerset operation in Python. I already had one cheap implementation in the video on hereditary finite sets, and in the last video where I demonstrated how to generate all the strings from an alphabet. I ended the video also in a very unaffected implementation of the power sets, where I just generated all the lists of objects that you can generate with a finite alphabet, and among those the power sets can be found. And if you filter out all the crap that you don't consider a subset of the original set, you get also a power set. But both of those were not so nice implementations, and what I actually wanted to do was going from Python to Haskell and Idris. And so in this video I will end with an implementation in Python that looks like the implementation that we're going to use in these functional languages. But we can point out more ideas along the way, and so this is what this video is going to be about. So without further ado, let's get into it. I will re-implement very quickly the operation that creates all the words of a given alphabet, right? That was in the last video. We had this function. I will in this video just call it words. We want all words of a given length of a given alphabet. Let's call it symbols. And in the previous video, but I coded the function in a way that it keeps on printing all the words. In this case, video, we don't need a print out. We just want the end result, and just the words of a given length. So this is actually a little bit quicker. We return the empty word that represents the empty word if the length is 0, right? There's only this one word with length 0, and otherwise there comes this recursive call, and I'm not going to describe it in much detail in this video. If you want to understand it, it's elaborated on in the last video. So how did it look like? -1. So what is happening here? Well, if I take this for a second here, if I remove the symbols thing, then this would just be the word itself, right? And since here I recursively generate all the symbols, I start with, I make this recursive by calling the words function on the shorter words, and then add at each iteration this new symbol for all symbols, right? So this is the function. And so let me give you an example. This is really just a repetition of what we had in the last video. So let's say the symbols, and I will foreshadowingly call them base here. Let's say the symbols is this list or tuple of 3 characters. It can be any characters. Let's take these. And the length, I will call exponent here, is, let's say, 3. Then what this function ought to do is give all words that you can build with the symbols, right? So let's call them combinations of the length exponent and of the symbols base. And let's print those. Print combinations, and let's also print the length of the combinations, right? So yeah, so you see, these are the words as lists of characters. I can also make this a little bit more readable by joining those together. Join for the combinations So you see I had this alphabet of 3 characters. I wanted maximal length of 3, and these are exactly these the words that you can build. If we go up to 4 here, let's say, well, we have more, of course. And I printed the length to point out how this is just the exponent, right? This is just 3, which is the length of base, to the power of the exponent. And in this way, the names make sense. So we can actually like check this. Is the length actually the length of the base to the power of the exponent? True. Okay, so this is the re-implementation of the thing we had before to document this, because this kind of scheme will pop up also in the Powerset in the various forms. So we consider length number of iterations, and then initialize. So this is the initialization, or add elements. So here is this addition of elements in each iteration, and the words that are already produced at each step are, the number of them is multiplied, you can say the length of the words, like these lists of words, is multiplied by the length of the symbols. And thus, if you do, let's say 5 iterations, then you would have the length of symbols times itself 4 respectively 5 times, so at each iteration. And this is how we end up with the exponentiation. Okay, so that for explanation's sake, I will actually comment this out, otherwise we would print this every time. So there's now a way we can actually use this small function, like this one-liner, to generate the power set of any set as well. And for this we just need this like basic observation. Let's say we have a set. Let's say I just write down some set. This is my set. The set of all numbers from 0 to 6 in this case. What is a power set? Well, let's just write down one power set, for example. So if I remove the 2 and the 5, right? So this would be obviously a subset, right? A subset is just another set which is at most as big as this set, but potentially lacks some elements. In this case, 2 elements are missing. And so this means actually the subset is basically a specification of what we want to keep and what we don't want to keep. And for this reason, we can implement a function that takes just some set and filters out given some specification. Okay, I'm going to do this. So I'm going to define a subset function that you call a list or a set of values. I call this VS for values, and then some choice. Going to see this is going to be a list of booleans, yes or no, if you want to keep it or not. And what does it do? Well, return the V for V in V's, but I'm actually going to return an index with that as well, an index in the V's, enumerate, and I'm just going to actually add this V if the choice at this index is true. So, for example, if V is 1, 2, 3, 4, and my choice, let's call this my choice. My choice is true, false, true, true. Then let's print subsets V's and my choice. Let's call this my V's. choice. Then obviously the subset specification via choice just filtered out that I don't want to keep the second element, and that's why this number 2 was removed, right? So we have now words and subset, and we can easily combine both of them to compute the power set. So how do we do that? Well, define a power set, or power operation on list in this case. I'm going to index this with a C for choice because I will have several power set operations implemented on some set. And what is this going to be? Well, I'm going to use the words function, right? I'm going now to generate a list of all possible options of true or false that correspond to some choice, and therefore I will fix as base the list true false, or let's actually go with false true. This just fixes the order in which the sets are going to be generated. Then my exponent is going to be the length of these, and I'm going to return, well, the power set is a bunch of subsets of VS, and the choices are going to be words for word in, well, exponent base. So this is my simple implementation. Let's check it out. Print power my v's, and let's also print the length of this thing, and I will comment out this example. Word is not defined, words. So, and here you see this is a set of length 16, so 2 to the power of 4. 4 happens to be the length of this set my v's. And if you take a look, this is exactly the power set. So I generated the power set without doing any overwork, also using this words function, and I just use the words function to generate all specifications. And for any finite length, these specifications exactly correspond to the power set of the finite set of that length, and that's how that works. So that was my first implementation of the power set operation. This looks pretty different than what I had previously. So if we go back to the power set operation that I had implemented in this video here, I have it saved actually in preparation. That's this one. So I just copy it now. Let's print like 4 dashes so that we see the separation. This was the implementation we had previously. Here I just reversed the ingoing list, but this is just so that the order is exactly the same as in the implementation here. That has no effect on the power set. It's just an ordering, and a set doesn't even have an inherent ordering. So I will first run it. Let's actually run it not on v's but on my v's. And then we see this is literally just the same result. So it's a different implementation, but another result. Let me quickly go through the implementation that we have here. So what's happened? So the difference is here we don't generate the choices and so on. Here we actually construct the power set as a set of subsets. We initialize, so the initialization is also there. We start with the empty word. This is basically corresponds to this one, right? And then we go through all elements in the original set that we want to take the power set of, and keep adding new subsets by taking all subsets that we already have and appending the new element that we go through here in the outer loop to this. And this way we also find all sets. This is the implementation that you will find. Like I quickly checked Wikipedia and came to the Stack Exchange thread where they implement subset in the Powerset in a similar fashion as an example. But this is arguably not so nice in the sense that you have these two for loops and so on and so forth. If you go on the Wikipedia page to Powerset, you also find actually in this article an implementation for an algorithm, or you find the algorithm. I just added the implementation there last week for how to recursively compute the power set operation, not going over the choices as we just did. And so while the two implementations that we have so far are nice and give the same result, there's the kind of more direct, straightforward one, and this is the one we're going to explain now, and finally then rewrite it in a way that makes it easy to implement it also in a functional language in a future video. So I actually also have this prepared here, but so just for the sake of comparison, I want to highlight how that actually works, like how this algorithm just computed what we have here. And so yeah, so let me make one observation. So let's actually, because this is a little bit long, let's actually remove the for here for the sake of the moment, so that we deal with a little bit shorter expressions here. So let's take this power set, right? So what we can see here actually is a separation in two parts. You know, the power set is always a power of 2, and we can make the occurrence of 2 actually a little bit more explicit. If you stare at this for a second, then you actually see that you can separate this into two sets. One is one not containing let's pick out the 3, not containing the 3 at all. So this is actually a subset of the power set 1 and 2. So this set, this contains a 3, this doesn't, this contains a 3, this doesn't, this contains a 3, this doesn't, and this contains a 3. And so this is a subset, and this here is this plus, well, this set here, right? So I just reordered it to highlight how taking out any element, in this case the 3, separates the power set into 2 parts, and this here can be rewritten as follows: s plus 3 for s in the set, right? And now the last thing we just need to observe is that this thing is actually the power set of 2, right? If P denotes the power set, and this is actually the power set of this list here. So this was the power set of 1, 2, 3, which is this, and here we see already the recursive structure, right? So to compute the power set of the 1 to 3, we just have to remove one element, compute the power set, and then take this power set and append also the element that we previously removed back to this set, right? And this is the way in which you can recursively now compute the power set. Of course, the power set of 1 and 2 is also the power set of the set containing just 1, and then the 2 added in this way. And this is the algorithm described on Wikipedia, right? This recursive algorithm. I have it here as well, and this is the one I wrote down on Wikipedia. So what does it do? Well, if the set that you pass is the empty set, well then the power set is just the set containing only the empty set. Otherwise, split your set in 2 parts, pick out any element. I pick out the first element here and the rest. Compute the power set of the rest, which is a recursive definition, like calling again this function. And then computing this augmented version of the power set where you add the E everywhere and return the whole thing, right? So if we try this out with the myVs, maybe for the sake of it, also print so. Then we see we have literally 3 times the same result, like for this wiki implementation, for the Stack Exchange implementation, and for this combinations implementation. Let's add another element back here. So, right, it's the exact same thing. And of course, you could do some fine details. You can, for example, if you like switch this up and do it like this, then it would give you the same thing as a set, but it would like flip the order around a little bit. This is the same thing, but maybe this, I'm not even sure if this does see anything out. No. Yeah, so the order is a little bit flipped up now. This is all this does. This doesn't really matter as far as sets are concerned. Maybe as far as lists are concerned, but not so much for sets. And all the ingredients that are highlighted here, I added this documentation, is to point out that in this Stack Exchange implementation, there are the same things going on here. The only difference is that here we have 2 for loops, and here we have a recursive call, right? Okay, and finally, we're going to do this implementation basically one more time, except now we make it even more like, let's say, functional, like Haskellian, functional programming suitable. I might just augment this actually, or let me do it like this. We define the power set, let's call it power set F for functional. So if v is the empty list, like I can write if v is the empty list, empty set. A little bit more fancy is maybe in Python if you do if there's nothing in there, you can also express it like that. Well, okay, we return this thing, we already had that. Otherwise, what we called T before, let's call it subs or subsets. Now this is going to be everything apart from the first element. And then, like in the functional spirit, I'm going to define a lambda expression, the prepend x expression, which is lambda sub. So this is a function that appends this first element, which was previously called E here, to the sub. I make this lambda expression because in Haskell this will actually just be a function of like 4 characters or so. This is like more suited for that. And now we define the subset with x added, and now we're going to map this function over the subs. Right, so this is basically this operation, but also in a more like maybe parallelizable way when you highlight that this is the map operation there, and we return subs plus list and this operation. Right, and of course, you know, for one thing, this is basically the same limitation as above. Like really not much change here. I can test it that indeed we have this same result. So now 4 times the same thing, and of course we can also, you know, make this much more compact. I mean, I introduced a bunch of expressions here. I don't have to. I can just go with this and go with this. Right. So this is also readable. I would argue, same thing. And if I really want to make it super compact, I could go with. I mean, then I have to rely on the compiler not to do computations more often if I remove the subs here, but this is also if these else check. So this is basically the one-liner Powerset operation, right? Okay, so I hope that was not too boring. There's all a purpose to introducing these objects because I'm going to use them. I sticked under half an hour again, so very glad. And that's it for today.